Hello, everyone, and welcome. Am I audible?
Yes.
Yes.
Okay. Thank you so much, everyone, for joining today, and special thanks to those who have taken the time to be a part of our very first webinar series of Geo-Lesson. So, Geo-Lesson was created as an educational outreach platform with the simple but important goal to make conversations around resilient and sustainable infrastructure more accessible beyond classrooms. So it's now my pleasure to introduce Dr. Sadiq Khan. Dr. Sadiq Khan is a geotechnical and geoenvironmental engineering researcher and associate professor of Jackson State University, whose work focuses on, but not limited to, infrastructure resilience, climate adaptive systems, field monitoring, and nature-based solutions. So today, Dr. Khan will be introducing Geo-Lesson webinar series, sharing insights in both research and real-world practices. And we are very grateful for his initiative and time for setting the platform for this new webinar series. So thank you again, everyone, for being here. We encourage you to engage, ask questions, and be a part of this conversation. So with that, I'll now hand it over to Dr. Khan.
Thank you, Adrika. Really appreciate that. Let me try to share my screen here first. Good morning, everyone. So in this webinar series, first of all, I would like to talk a few things about a Geo-Lesson. And then after Geo-Lesson, I wanted to move forward with our presentation and what is our end goal here. So we wanted to take many of the ideas that we are currently working on, and not only us, but others who are currently targeting different work on the sustainability and resilience for the geo-infrastructure. So the sustainability and resilience both are very hot topic, and there are like many work that has not been taken to the broader community. So we believe that is really important to educate everyone, and we also believe that this learning should be done in a way it is accessible to everyone. So that's that's why we started the Geo-Lesson. The goal of Geo-Lesson is to transfer the education free to the practitioners, and our goal is or taking the learning from the practitioners to the students. So it goes either way. And so today I wanted to give you a very uh, broader perspective of what is the resilience and how the resilience is needed, how we can create the resilience, and we can move on from here. It's still very early stage work that we have done from our group, but we wanted to extend it, and we also encourage questions, comments, and insights from our guest, because I truly believe that it is a huge topic, and it needed uh, the learning and the experience from everyone. So if you look at my screen has a failure of a highway site, which is State Highway 26, has a failure during the time of Hurricane Ida. And this is a really interesting site. Uh, and I'll try to share some information on that. So here's my background. I believe most of you knows about my background, so I'm not going to spend much time on that. I would like to spend some time on this slide, which is on the what is happening in our precipitation change and how this precipitation changes is happening over the time. The way it works, if you look at this is the change in terms of this is the difference. Like it is showing the change, and like it's up to 10% change. But even if we look into the 10% change, this is annual average precipitation. So the average precipitation, the way it works is like that this is the total change. But the total change doesn't represent the individual extreme events. So if we compare the precipitation data back on 1900 versus the precipitation data in last 30 years, the thing that we can see is our rainfall pattern has changed significantly, especially it is moving toward the eastern side from the western side. So when the precipitation is changing from the eastern side to the western side, it the western side is not getting enough rainfall, and at the same time, it is getting drier and is getting like some drought type of scenario. And on the eastern side, it is having like more rainfall. More rainfall means it will has more volume. So the more volume also creates some other challenges too. For example, flooding, erosions, all sort of the challenges, right? Then we look into the changes in the temperature and the way that the temperature uh, works. Basically, you can look into the way the temperature here in 1900 versus the temperature in the last 30 years. You can see we can draw another line and at the middle, and we can see that the temperature on the right side or the eastern side has not have significant change, but on the western side has a significant change. So now if we look at the western side of it, we are seeing there is a there is increase in the temperature, and then there is a increase in terms of uh, the rainfall from the previous slide, right? So on the western side, there is increase in the temperature and decrease in the rainfall. On the eastern side, there is an increase in the rainfall and the temperature remains same. Okay. So in and all of that has some effect on our infrastructure system. Uh, so now we are facing so many extreme events. It includes the flooding, drought, wildfire, and snowstorms. Flooding, where we have more rain, drought, where we have less rain and high temperature, wildfire, if we have a prolonged time of the drought, as well as if there is a kicking of the fire, which happened in California in LA fire like last year, becomes a big news. But there are like so many wildfires always happening. And then when there is a wildfire also creates so many failures. And one of the major outcome of the wildfire is landslide. That's really interesting. No one expect that there is a landslide from the wildfire, but there is always a landslide from the wildfire. And then the snowstorm. And in Mississippi, you all know, and in Tennessee, you also know what is the current impact now, right? So the question is, and then we also have the hurricanes, and what we are seeing that the hurricanes are becoming very, very powerful, very, very stronger all the time, right? In the last 5 years or last 10 years, if you look at all the hurricanes become super powerful. So whenever there is a hurricane coming in, all the hurricane create a significant damage and create a significant toll. So beside the hurricane, let's say if we look at any of the hurricane here, for example, if we are looking into Hurricane Ida here, now Hurricane Ida came in through, it has the heat through the Baton Rouge, and then it went through all the way toward, like it started from Baton Rouge area, and then it passed through all the area, like some part of Mississippi, and then all the way it ended up in California, in like New York, New Jersey, this area, right? But whenever there is a hurricane, we always talk about the extreme event, the coastal flooding and the wind, where it get hit. But one thing we usually don't talk about, and which is also very, very important, is the amount of rain it brings on the table. And we just talk about the average change on our rainfall pattern, which is like around 10%, right? But during the time of a hurricane, there is a significant amount of rain. And this amount varied between 10 to 20 inch, where our annual rainfall volume is close to like 62 to 80 inch in many places in US. So if our rainfall is between 60 and 80 inch versus uh, we just received like 20 inch of rainfall or 10 inch of rainfall within a day or within a couple of days, that creates a significant toll to our infrastructure system. Our infrastructure system is not designed for that. So that is one challenge. And because of that, what we always see is the failure or the roadway washout, which created the challenges in terms of the washout. It created challenges in terms of our highway system, our levees, our dam, our railroads. And once the challenge or the once the damage has been done, it takes years to fix. So if we want to talk about the resilience, then we should also talk about why this problem is here and how this problem is coming in. So it's not only the roadway washout, we also have it has a significant effect on the slope. So there is one thing. The washout and the slope failures are different problem. Washout is one type of the problem where the water is coming in and water is taking off everything. It just wipe out the section of the roadway or the levees. So that is the washout problem. The landslide problem is a different problem. What happens is like whenever there is a slope, it absorbs more water, and that more water creates some problem there, and it create another sort of the failure, which is a slope failure. The next problem that it also create is a significant erosion and scour. And the significant erosion and scour is is there, and I know many duties or many cities are facing significant challenges to handle all the scour problem, the erosion problem, the slope failure problem, or the washout problem. And these four problems are very prominent into the geo-infrastructure system. So the question is how we go for the resilience and what is the gap in this system. And then what we are facing now is a new add-on. So the new add-on is the extreme cold. If you see this image in Minnesota, that is okay. But if you're seeing this image in I-55 in Mississippi, that's quite alarming. And the snow is sitting here for a week. It's not melting, and it's not snow, it's ice. And the photo on the right is in the Oxford, Mississippi. And if you look at this photo, at first I thought it's taken from the movie Frozen. It exactly looks like the movie Frozen, but uh, it's literally there. Now, what is the challenge here? It's not like it's new. There are many states facing snow or icing versus what is the challenge if Mississippi is facing it or Texas is facing it. The challenge is when we are getting the snow in Texas or Mississippi, our infrastructure system is not designed for this type of the snow. It's a additional thing that is coming to it. Our infrastructure system doesn't designed with the support system or whatever the the adjustment is needed into our slopes or our roads or our pavements. So it accelerates the damage. And I'll go there very shortly. So first of all, we just talk about there is a change in the temperature. There is a significant change in the rainfall. So whenever there is a change in the temperature and the rainfall, we need to look into uh, the the very basic. So first of all, what happens whenever we are seeing all the extreme event? The question is why we are having all the extreme events or why we are looking into all the climate extremes. The first thing what happens here is the temperature. Since the temperature goes up, uh, or if there is a rise in temperature, the moisture carrying capacity of air goes up to 7%. So when the moisture goes up to 7%, or the moisture carrying capacity goes up to 7%, the air can hold more moisture in it. And when air can hold more moisture, it has more evaporation because the temperature is high. So when it has a more evapotranspiration, then it will have more evaporation, more rainfall, more cloud, and then it is within the same time. So it's not changing the time from the starting point, but the time remains same. So the rate of the evaporation is higher, meaning we will have more moisture into the system. If we have more moisture into the system, we have more cloud, more rainfall, and more extreme event. So now the question is why we have the snow, or why we have the um, more extreme event, like more hurricanes. One answer to it, I'm not a climate scientist, but what answer to it is the amount of the energy that has been stored and the amount of energy that is being dissipated into the system create this challenge. Now, the way it works is whenever we are looking into the changes, like for example, now we have an average temperature of, let's say, 65 degree Fahrenheit in Jackson, Mississippi. So if this average temperature of 65 degree goes up from 65 to 66 degree Fahrenheit or 67 degree Fahrenheit, then what will happen is the moisture carrying capacity will increase significantly, because with that, if it already increased 1 degree Celsius or close to 2 degree Fahrenheit, the temperature, sorry, the moisture carrying capacity goes up 7% to 15%. And if it goes from 7% to 15%, now we have 15% more moisture. If we are having 15% more moisture, that will also create some challenges on it. And it will drag more moisture, and it will make more aggressive climatic event. So those are highly interconnected with the temperature increase. So what we are facing, the extreme events, are the results of the change in the temperature, which we used to call it like the change in the system dynamics. And every time the temperature is going up, our system dynamics will recalibrate. And if the system dynamics is recalibrated, it becomes very difficult to predict how the system will perform in the future because our loading behavior is changing. So there has been like some unprecedented rainfall, unprecedented flooding, and the washout. And the challenge is what we face is like whenever we are looking into the extreme event, it just come in for a certain time, it and then it's gone and everything becomes very normal. So we come back to our normal life and then we wait for the next event to happen. So if we are looking into most of the cases, what happens is these extreme events are not very uncommon. Extreme events happen in the climate, and it was there for a longer time, right? But the way we handle it is we usually handle it without return period in the design. The way it works is like we consider 5-year return period, 10-year return period, 50-year return period, 100 years return period, 500 years return period. Most of the extreme events that we are facing are coming from the 500-year return period or 1,000-year return period. But the frequency of this 1,000-year return period is no longer in 1,000 years. It is becoming more frequent. So, for example, if we saw the hurricanes with category 4, which usually comes back in every 100 years, now they're coming back in within 10 years, or they're coming back in 5 years, right? So if you are looking into the amount of the loading that is coming in, that it's supposed to come back in 100 years, now they're coming back in 50 years or even 10 years, it requires a significant investment into the infrastructure because now the frequency of the extreme load has gone up significantly. So if the frequency of the extreme load is going up significantly, it is also going to need more intervention. Is going beyond the point where we can ignore the effect of the extreme event, and we need to accommodate it in our design. Otherwise, we are going to see all the cascading failures that is coming back at different time. So here is the major problem, or here is the major gap that we really need to solve. So the first one is we have a highway system, or we have our roads, levees, dams built primarily between 1950s, 1960s, 1970s. Our interstate system are being designed and built around 1970s, and they are there. So we are already on 50-year plus time period on that. So we are facing the aging infrastructure problem. Then what we also have is like most of our infrastructure system, when it is being designed, they're being designed considering the data set from the past, meaning we use the data from 1930 or 1940 to 1970 and use this data to predict what is going to happen in the next. And let's say we did a really good job in terms of predicting what is going to happen. But even if we have done a really good job in predicting, our climate dynamics has changed. So if our system dynamics and the climate dynamics has changed and that the temperature is keep rising, it is going to change our water cycle. If our water cycle is changing, then it will change everything. It will change our soil moisture behavior. It will change the rainfall, evaporation, evapotranspiration, everything. Okay. Now let's look into let's look into deep into the problem. Let's say we are currently in 2025. In 2025, our temperature is 78 on average. Let's say from average temperature 78 to in 2050, our temperature is going to be 80. So from 78 to 80, we're going to have 2 more degree Fahrenheit goes up. And this is based on uh, the, the, the emission projection, uh, like on average, with the current trajectory. With the current trajectory, the temperature goes up with, let's say, 80. The weight is increasing in terms of the emission. The temperature will rise another 4 to 5 degree with this current trajectory. If we can, uh, but I really don't think that we can undo it. It's quite impossible to undo it because of the way we consume our energy. So if we cannot undo it, it is very likely the temperature rise will be around 4 degree Fahrenheit in next 20 to 25 years. So along this process, it's not from one step to another, it's a continuous change. So which means the system will continuously recalibrate, and our climate will recalibrate into that system within that time period, right? So if it is recalibrating within this time period, that means our prediction system becomes very, very difficult, because it is going to be very challenging to predict how it will behave in next 10 years or next 20 years. So that create a major challenge, because the way we usually design our infrastructure system, uh, it, we always try to predict a most critical scenario, and then we try to do the design or maintenance considering that critical scenario. But the critical scenario is not becoming the critical scenario now. Our critical scenario is changing over the years. So if our critical scenario is changing, then it is becoming very difficult to predict our operational condition. And that's a really great topic of research. how we can do the design or how we can make it work in terms of uh, the unknowns that we don't know. And then we also have seen that there are like the failures, and when the failure happens, this is really interesting. Most of the cases, the failure dynamics has changed. For example, what we are seeing here, there is a dam failure. So after dam failure, the water is going out, and this is a highway embankment failure. So when there is a highway embankment failure, the failure is very likely very similar to the dam failure, right? But the system is not, a highway embankment is not being designed to work like a dam. But in terms of the operational condition, it has some water coming in, and water is sitting on the back during an extreme event, and it is kind of pushing the water out and creating all the challenges. So now the question is, if we wanted to create the resiliency, uh, and how we can create the resiliency here. So the first of all, if we have wanted to make our infrastructure system more resilient, the things that we need is we need to know uh, how our system dynamics will change, which is quite impossible to do, right? If it is becoming very difficult, then our conventional system of design uh, becomes a bit challenging. The question is why? The answer is our infrastructure system, especially if we look into the gray infrastructure uh, system, the gray infrastructure system requires a specific design or targeting a specific scenario. So let's say we wanted to do the design on a highway embankment or a levee for 2050. So it becoming very difficult to predict how the system will perform in 2050. And so if we wanted to build a dam or a concrete structure, or we wanted to build like some other structure, that becomes very much static, which is great to start with. But if we can build a system, the system is very much adaptive, then it will help us to solve many problems. So in terms of that, in the infrastructure system, what we can do is beside our conventional system, we cannot replace our conventional system. Our conventional system will be there. But beside our conventional system, we should also start adopting more adaptive system. So one of the most adaptive system that is needed for the resiliency is the nature-based system. Now, the question is why we need a nature-based system. Basically, the nature-based system always adapt with the nature. So if our rainfall volume is changing, the nature itself will keep adapting with it because the nature-based system has the inbuilt adaptation in it. And it's a live matter. So when we are doing the design or doing the maintenance with the nature-based system with the live matter, it helps us to make the system more resilient right away. It allows the flexible design and it allows mitigating the load. On the other hand, if you're going to do the design with the conventional system is always taking the load and taking the hit. So if you want to create the resiliency, the first thing that we have to do is we need to understand uh, what is our challenges. So we need to know what is our current hotspot area. Second, we need to know is like how the system is performing. We also need to know how the system will perform in the future, which means we need prediction. And then from there, we need some kind of toolbox for the early warning. So the toolbox for the early warning includes uh, the system that requires uh, the proactive asset management. Now, the proactive asset management is sometimes a vague term because whenever we are talking about the point that we need to be proactive, we all understand that being proactive is the best possible way to do it. but it's not easy because we really have to know uh, the 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 point where we need to do some work or maintenance. And I believe that that's a $1 billion question, because if we can identify that this is the point we should do some maintenance, then there is a question comes in, that is it the right time? Are we overestimating or we are underestimating? And then at the same time, we also need to have another thing is we need to have a very low cost solution for this. So if we are not coming up with a very low cost solution, we cannot make it work. So far from our team, we have done some work with the pin and vetiver. I will have some example of that, but eventually that's not the only solution. There are many other solutions, and every solution has to be evaluated in a similar fashion. But before going there, I wanted to highlight few things. And the first one is I wanted to see, and I wanted to present like how the system dynamics is changing. So we have done some work on the slopes in Mississippi, and what we have seen is like we look into the performance of the moisture change, and what we noticed, because there is a higher amount of rainfall, the soil try to keep more moisture in place. And we are not seeing significant changes in the moisture, but we are seeing that the soil is holding the moisture, and it becomes like very uncommon behavior. Usually we expect, especially in the expansive soil, we are seeing that the temperature and moisture is changing, but in terms of the soil moisture, it's not changing that much. We also have looked into it in terms of adding the rainfall boundary, and see is like what is the impact of the additional rainfall, what is the impact of the temperature and so on. And what we have seen is like at different time, we can predict is like how the system, how the factor set of the system is changing, and because of that, how uh, the failure will happen. So we can predict the failure if we can incorporate the loading of the rainfall and other environmental aspect into our system, and we can go from there. Then what we are also seeing that the whole system performance is changing in terms of the infiltration behavior is changing our at different climate or at different time after the climate. So if our infiltration behavior is changing, we cannot build the system only with uh, the buttress type of method where the dynamics will change. So if we move from the static to the dynamic adaptation technique, the nature-based solution will give us a huge benefit on that. The another aspect of it is on the soil and material properties. So what happens? First of all, we are looking into our soil types. Every soil types will face some of the changes because our temperature behavior is changing, our rainfall behavior is changing, so our wetting and drying cycle is changing, and then we are getting the snow. So when we are getting the snow, we will also see that there is a wet dry cycle and there is a freeze thaw cycle. So now in Mississippi, we are going to have a freeze thaw cycle in within next 3 years. So most of our system is not supposed to face the freeze thaw cycle, but now it is facing the freeze thaw cycle. So if it is facing the wet dry cycle along with the freeze thaw cycle, the the microstructure of the soil or the microstructure of the material, whatever material we're using, we can use the pavement, and within the pavement it is also changing, is gonna change. So if that system is changing, then we will see quicker softening or quicker weathering action that we didn't expected it. And it will have some impact on the system. So if we want to build the geo-infrastructure, and here I am more interested to talk about the geo-infrastructure because this is kind of like our major focus area. So in terms of our geo-infrastructure, the temperature will change. So when the temperature will change, we need to accommodate the changes that's going to happen in terms of the material properties, the infiltration behavior, the factor of safety, and so on. And if you wanna incorporate that, then if we wanna create a resilient infrastructure framework, what we have to do is we need to adopt some of the plan that requires first, we need to have a understanding of the exposure. Like we need to know our current infrastructure system, how it is built and how it is going to perform. The second one is to look into the asset vulnerability or looking into the risk, like what is the risk going to happen. Then we also have to look into the future options. And one of the most missing component in our design is we don't look into the different climatic scenario. Our design method requires or the code requires to consider a very specific condition. But we don't always face the very specific condition. There is a big gap between our design load versus what load we are facing. And if you want to incorporate that, uh, I think it is very important to integrate whatever the challenges, the real challenges may come in, and we should run some scenario with that as well. And then the most effective one is if we can take some proactive action, because the proactive action help us to mitigate the failures. There is a futuristic design and operation for resiliency. Uh, the most important one, if you wanna just go for the resilient infrastructure design, what we propose to do is first we need to look into the integration of the climate what if scenario. The second one is to look into if we have any chances of the flooding scenario. And I'm talking this one mostly on the roadway, because what happens for the roadway is roadway system is not designed for flooding. Roadway design system is not designed to retain water. But there are many cases now because of the change in the system dynamics, the roadway has to retain some water. So if we wanted to retain some water, are we designing it to consider how to retain the water? This, then we need to look into if there will be any changes in terms of the soil properties, in terms of the material properties, because that also creates some effect on it. The next one is, are we ensuring adequate drainage? And the last but not the least is we should be incorporating a monitoring system. And the monitoring system should be integrated into our design because we don't know how the system performance is going to be. So if we don't know how the system performance is going to be, it is better to know beforehand how or the most critical sections behavior so that we can take proactive action. Because without data, there is no way we can move for some proactive actions. We have done other work, and if any one of you are interested to know, I can share you this report. This is one of the report that we have done with MDOT State Study 286. So on that one, we have looked into the expansive soil, which is Yazoo clay. We look into it at different time with different wet dry cycles and the weathering behavior. And then we also look into it from the different effect of the rainfall. And when we look into that, we have seen at certain condition, it is going to predict the most critical scenario where the slopes are going to move or going to fail. And considering that, we recommended to MDOT what is the best scenario to go for the preventive maintenance for the slope on expansive soil. So in terms of the way it works is like within 7 to 10 years after compaction, if it's a compacted slope or like a field slope, they usually face some kind of movement within the slope. And we have different options to repair that. In I'm gonna cover pin and vetiver in a bit, but basically these two are like can be a really good option for the proactive maintenance or the preventive maintenance. And I wanted to highlight why. So pin, the way pin works is like pin is made from recycled plastics. We can push it into the ground, and it helps us to do a quick fix. But pin has a one major benefit, and this is a huge benefit, which is we don't need to move the soil, or we don't need to take the soil away from the site, bring new materials in, and do something. Instead, what we can do is like we can just use the existing slide, push it back, recompact it, and install the bin. So this method is way faster and quicker than the traditional slope repair technique. And since it can be installed very quickly, the cost of the repair is very cheap and way cheaper than the traditional method. And then it is also quite faster to build within a short period of time. So eventually or ultimately, it can be used as a proactive maintenance. Because if you're going to go for a proactive maintenance, we really need two things. One, it has to be cost effective. And the another one is we need to do it with the existing grading of the slope. We don't want any earthwork when we are going for preventive maintenance. If we see that the condition of the slope is dropping, we should come back and we should do some work so that we just enhance the lifetime. And pin can be a terrific choice for that, from that from that perspective. The another one is here are some of the photos of the pin where we primarily used it for the preventative measure. We also have the vetiver grass. The vetiver grass, the way vetiver offers, it's a terrific methodology. It has a significant benefit in terms of the root strength. It also takes the moisture out from the slope, and when it does, it also undo the problem that the because of the change in the system dynamics, whatever the challenge we are facing. So putting the vetiver grass is kind of going to undo the behavior of the slope and make it resilient the way it should be. And we will have in the Geo-Lesson, we will have at least two or three more presentations on the vetiver grass, like the way we tested it out, the field testing method, and all the details. And it should be coming up in our future webinars. I believe our next presentation is going to be on the vetiver grass use in the slope. Uh, Here are some of the photos of the stabilization of vetiver grass in the US-49 site. We planted 5,000 plants. We are monitoring it for around 4 years. And in this slide, we have like three different sections. One section has like some of the movement. The second section has a complete failure. The third section was kind of like in a marginal condition, and we planted vetiver, all three, monitored it, tested the data, and it moves on. And it was a really low-cost solution compared to any other traditional methods. It takes like a year to establish the root system, and as soon as the root is working, the system works great. Here are some of the results of like what happens before and after vetiver. So in the same section of vetiver where we planted, we can look into our moisture distribution, and then what happens after vetiver plantation, like within 6 months, we see there are some changes into the moisture on the top. And because there are some changes in the moisture on the top, uh, it is kind of drying out the slope. And when it is drying out the slope, it helps us to increase the factor safety of the slope. There are some other example of using vetiver on the Gulf Coast. Uh, I met a guy who used vetiver to mitigate the erosions into the like his land. He's trying to save his land here, and then this is on the Gulf, so it is usually faced the tidal flooding, and so the tidal flooding is a repetitive flooding comes in. So what happens there is the vetiver has the root system of vetiver can kind of create a barrier, and it doesn't let anything comes through it. So if you see that the root behavior, this root is kind of holding it, and it create a line. It's like it create a barrier. So soil that doesn't go away with the washout. And this is a great learning for the to build a system for the washout. Basically, the way it works is this plantation was done on 2009, and I took this photo into 2025. So for 16 years, it has been there, and it was able to cut off any of the erosions after the grass. That is amazing. And so as I mentioned, is like if you want to go for a proactive repair using vetiver grass, we have to follow those four techniques, including understanding the problem, know the current condition, do the design, and then going for the intervention. So, and vetiver can be a really great choice for that. Vetiver also here, like vetiver is not a solution for all sites or the all states, but it works in from Texas all the way to not like the south of Virginia, including Florida, and then vetiver also works in California, Oregon, and Washington. The most interesting thing is I pulled up the climate data and the normal precipitation annual, and you can see is like the areas where we are planting the vetiver, both all of them has the moisture problem. It's not a drought problem, but vetiver also works into the drought because vetiver is one of the plant which is extremely surviving and can survive in very extreme climate. That's my presentation for today. I would like to acknowledge NSF, Gulf Research Program, MDOT, and Use Duty for funding it. And I would like to open up the question. I think we have 8 minutes for the questions.
Can I ask a question, Dr. Khan?
Sure.
So, with the thing that you were saying that with the changes of the precipitation and the temperature, I mean the climate pattern is changing. So, how do you think that we should deal with the existing structure that was designed before, not for the adaptation of the changes of the temperature?
Mhm.
How we want to like, what should be our approach for the existing structure?
That's
We
a
can
really
design
good
for the
question.
new structure, but the existing one, how should we retrofit them, or should we, what kind of measures or we should take for
First
the
of all,
variability?
okay. That's a really great question. What we need to do is we need to understand the critical things, the critical behavior. Now, the way we did it, let's say when we design our system, the system our design technique might be 80 to 90% accurate. So that way we are able to predict like this behavior will be there, right? But now because there is a climate change and it is changing the system, so that accuracy level may have gone down, right? It might not be at 80% range, but it might be at 50 to 60% range, very likely. So, and that's why what we are facing is whenever there is a extreme event is coming in, we are kind of like submissing ourselves to that. So if you want to update it, the first thing is we need to know the most critical vulnerable spot. We need to do some kind of modeling and we need to predict like which part of the section is going to be most vulnerable. There are like different learning that we have learned so far. So we can incorporate those learning to predict which part of the system are bad or which part of the system is not bad. That's number one. Number two, we need to know the overall system's performance. If we know the overall system performance, we can enhance the performance. The first thing is we need to know the most critical spot. We should retrofit those spots, and then we should have a continuous monitoring on it. So the asset management is a really critical need now. Asset management could have been ignored before because the system was performing really well. You don't need to spend any extra money for that. But whenever your system is being designed and your operational condition has changed, so your asset management becomes super critical. And when you have the effective asset management in place, you know your inventory, you know which asset is not performing well or critical, and then you do the intervention. Third is we have to take the proactive measure, not the reactive measure. If we are taking the reactive measure, our cost will be extremely high. We cannot afford it. So if we want to have a affordable way of maintaining it, we really have to identify the problem, and then we have to repair it in a proactive manner, not in a reactive manner. And to do it in a proactive manner, we really need to have a really good predictive system. So, and we can only build a really good predictive system if we have a continuous flow of data. So the continuous flow of the data is super critical here. This is one of the most critical thing that we gonna need is the data. And in terms of this, we really need to learn how to incorporate the data into the system, and then how we do the data driven design or the data driven maintenance or management. And then the nature-based solution is a really great tool or technology to mitigate the problem, because nature-based solution will extend the life of the system no matter what. We cannot do it with our traditional method. Let's say I have seen some people are doing the design with like a failure, they just build a retaining wall. Building a retaining wall is not an adaptive system. We are predicting it for the next 5 or 10 years is gonna work. But if you are going with even the plastic pin is not the best solution for this, but vetiver or any other solution, like any other nature solution, that is needed. And there is a huge need in terms of what nature-based solution is applicable for what problem. So, for example, vetiver, if you look at vetiver, only work in certain state, right? But this problem exists everywhere. So the question is how we are looking into the other states, or what problem, or like what solution we can bring on the table. See, some solution similar to vetiver. That is really important.
Thank you.
Dr. Khan, I have one more question. Uh, am I audible?
Yes.
Yeah.
Yes.
So you mentioned that there will be a freeze and thaw cycle. So what will be the impact on the pin or whatever in that case?
Vetiver will survive. Vetiver usually, if the land is not fully frozen, the soil is not frozen, right? Even though we are frozen, it has to be a thaw for a certain time, let's say a month, couple of months, to kill vetiver. So the icing or like the top part has to be frozen, completely frozen to kill vetiver. So vetiver will survive. For pin, it may change its creeping behavior. Its material behavior may change. We haven't tested it. And we haven't tested it how our whole roadbed is going to perform. But I guarantee that the entire roadways that faced this thawing cycle is going to deteriorate much faster. And it cut down its lifetime at least 20 to 30% just by one cycle of freezing and thawing, no matter what.
Thank you.
Sure.
Hello, Dr. Khan.
Hi.
Hi, may I ask what are the concepts that we will learn in the future Geo-Lesson classes?
What we can learn in the future, Geo-Lesson? Say it again. Sorry, I
Uh,
missed it.
can you tell us what we are gonna learn in the next Geo-Lesson classes?
Yeah, in the next Geo-Lesson, basically in terms of the Geo-Lesson, this is our first class, first webinar, not a class, webinar. And the next webinar, we wanted to have it on vetiver. So in terms of vetiver, we're gonna have like two more. One is vetiver for slopes, and then vetiver for phyto remediation. So that's going to be our next two. Then we are going to move to the data. So in terms of the data, we are going to incorporate like there are different techniques on how to use the data to do the design. So like the data-driven design, how to incorporate the AI models, how to build the AI models, all sort of the thing. That's going to be like another three or four. And then we are looking into there are some other techniques like the geophysical testing, geophysical method, LiDAR drone analytics. We are going to have like a couple of presentation on that or webinar on that. And then we wanted to move toward the sustainability topic. So the sustainability topic includes the topic include like what are the environmental challenges is there, how we can make it more sustainable, how to incorporate the circular economy concept into our infrastructure design, what are the like some case studies like that. So in next, we have the plan for next 3 months for now. And then we also wanted to go from there. And we also wanted to see is like if anyone else outside from our group are interested to present and show their case studies. And I would like to welcome that as well. We also wanted to make some invited presentation or invited webinar. We wanted to focus primarily on the resilience and sustainability. So any topic that fit in there, any case studies that fit in there, targeting the resilience or the sustainability would be our topic.
Oh, okay, thank you.
You're welcome. I think we can take one last question if it is possible, because we start 5 minutes late. All right. I think that's all. Atrika, it's yours.
Can you please share the presentation with us? And the
Yeah,
PowerPoint.
we'll post it in the Geo-Lesson.
Okay, sure.
Thank you, Dr. Khan, for your wonderful presentation. And before wrapping up, I would like to thank you all again for joining us today and being part of the very first webinar series of Geo-Lesson. So to end this, we will share the PDH link with detailed instructions for those who claimed for the PDH requirements. And we truly appreciate your engagement, questions, and participations today. So your involvement is what truly makes this learning community meaningful. So thank you for your time, and we all hope to see you again in our next webinar in February.
Do
Thank
you have the time for February?
Not yet. We'll probably post it from our.
Sure. I think that the best idea is this timeline is pretty good in terms of Friday, the last Friday of the month. So we can target the last Friday of the month. And I have seen like some participants from Bangladesh, so that is also awesome. So this time might be better. It's like Friday night at Bangladesh, 11 a.m. or 11 p.m. So that might be okay. All right. Thank you.
Thank you, everyone, for joining again.
Thank you.
Thank you.
Thank you, Dr. Khan.
Thank you.
Thank you, Dr. Khan.
Thank you.